In today's video, we're going to talk about bipolar transistor biasing and beta dependence of that bias point. Now, the bias point of a transistor is also known as the operating point or the quiescent point or Q point, or sometimes just called bias point. And it's effectively, the voltages and currents associated with the transistor in a circuit before you even apply a signal to it. When the transistor is used as a switch, it's not typically that important. But when it's used as an amplifier or many other applications, the bias point is going to control the performance of that circuit, so it's important to have a bias point that is predictable. Now, many people, when they start to set up the bias point, will start considering beta, or the current gain of the transistor, and use that when trying to figure out how to set up the bias point. The problem with that is that beta can vary a lot, from device to device, versus collector current, versus collector emitter voltage, and even versus temperature. So if you want to build a lot of a particular design, or you want other people to duplicate the design, you don't want your circuit to have a lot of dependence on beta, so that when the circuit is replicated many times, it'll always perform the same way. So there are ways of setting up bias, or the Q point of a transistor circuit, that to reduce the dependence on the current gain, or beta. There are many ways to set up the bias on a transistor. We're going to look at just 3 examples and take a look at how variations in beta will affect the bias point, or Q point, established by each of those 3 circuits. So we're going to pick 3 transistors, basically very similar transistors, but with 3 different values of beta, and plug each of those into each of these 3 circuits and look at how the desired bias point, or voltage across the load resistor, varies as a function of that beta value. So for our application here today, here's our example requirements of where we want the bias point, or Q point, to be. We're going to use a supply voltage of 9 volts. We're going to have a transistor biased with about 4 volts across a 3.9K collector resistor. And the reason I chose this is it's pretty typical. If you had a 9-volt supply and wanted to use this transistor as an amplifier, you'd want this collector voltage to be somewhere midpoint between the positive supply and the saturation voltage of the transistor to give you the maximum available swing for that transistor to operate, say, as an amplifier. So that's a pretty common requirement. So if I know I wanted the load impedance to be 3.9 k ohms, I wanted about 4 volts across that, it means I need about 1 milliamp of collector current. So those are our starting requirements. So let's take a look at setting that up with our 3 circuits. Okay, so let's measure the beta of each of our 3 test transistors here. Adjust the calibration on the meter here. And this nominal, first one we'll call nominal, is just shy of 180. We'll just call it 180. So record that value here. The next transistor, same type, but just from a different lot. Let's adjust the calibration on this one here. And beta, this one is, looks like about 115. So we'll record that as 115. And then our third one is right here. Let's adjust the calibration on this one here. Back a little bit. And looks like this one is close to, I don't know, we'll call that 275. 275. But one thing to remember before we get started here is that these values of beta are at the particular test current that my transistor checker uses, which isn't going to match the current that we're setting up in our circuits here. So the actual current gain, or beta, is going to be different in our test circuit. But we can use these as good relative indicators of the difference in beta between the 3 transistors. Okay, this first circuit simply puts a resistor between VCC and the base to set up a fixed base current. That's going to set up a fixed collector current and then generate the voltage across the resistor. So we'll put our first transistor, the nominal one, in place and measure the voltage here. We're looking at about 4.02 volts. So we'll record that as 4.02. Next, let's grab the resistor with the low beta value, stick that in there, and measure our resulting voltage. We can see this one measures about 2.98. So quite a big difference, 2.98. Okay, of course that with the lower beta value for that same base current, we're getting less collector current, so less voltage across that resistor. Now if we take the transistor with the highest beta, we expect to see the largest voltage drop across that resistor. In this case we're looking at about 8.69 or 8.69 volts. So a lot of collector current and basically just about saturating that transistor. So we can see that this very simple, fixed base bias circuit does not do a very good job in giving us our desired Q point with transistors that have got different beta values. So not a very good choice for giving us a nice stable bias point. This next bias arrangement can be called collector feedback bias. Instead of taking the base resistor and going right to VCC, we bring the other end of it to the collector. Now let's see how this works. Let's say for a given base current, okay, therefore a given voltage across this resistor, we're going to have everything kind of stable. If the beta were, say, to increase, all right, that increase for the given base current would cause the collector current to increase, which would pull this node down because it would drop more voltage across the collector resistor. As this node gets pulled down, that would reduce the voltage across this resistor, thus reducing the base current. So it would tend to limit how far down that gets pulled. And vice versa, if beta were to decrease, this voltage would tend to rise up, thereby increasing the base current to compensate. So this circuit will somewhat compensate for changes in beta. And let's see how that works in the measurements. All right, starting off with the nominal transistor in place. We'll measure the voltage across the collector resistor, and we can see about, call that 3.86. I'll record 3.86. Let's grab the resistor with the low beta, or excuse me, transistor with the low beta, stick it in there, and measure that voltage. And now we're looking at, let's call that 3.28. 3.28 volts. So not a huge change, not as much as we saw in the previous circuit. Now let's grab the high beta transistor, stick that in here, and measure that voltage here. And we're looking at about 5.50. Call it 5.50. Now comparing these two results, we can see that we had a huge change, a 4-volt change between nominal and high, and about a 1 volt change between nominal and low. And here I've got a little less than a 2 volt change from nominal to high, and well under a volt change from nominal to low. So much less variation for the variations in beta. So we're going in the right direction. Now this is often used, and you see this in many circuits. One downside to this circuit though is that this feedback element that's here is also going to affect the gain. All right, it's basically a feedback element that can sometimes be incorporated into the design of the amplifier, and it'll work just fine. But other times it might be a problem. But this is a very common arrangement for setting up a bias that is reasonably immune to beta. It's certainly not entirely immune to beta, but it's certainly better than a fixed base bias. So let's look at the third result. This third bias arrangement we can call a voltage divider bias, and it reduces the dependence on beta by essentially taking the base current somewhat out of the picture. And it does so by setting up a voltage divider where the current going through that divider is much, much greater than the base current. So any changes in base current that are a function of beta are not going to affect this voltage divider much. So this voltage here at the base basically stays pretty constant even if you have a change in base current or a change in beta. So with that fixed voltage at the base, it also establishes basically a fixed voltage across this emitter resistor because VBE is going to be relatively constant as well. So with that fixed voltage on VBE, we can basically pick this resistor value to set up the current that we want here. The emitter current is pretty close to the collector current, so now that everything is basically going to be pretty fixed. So let's go take a look at the measured results using this bias arrangement. Okay, sticking the nominal transistor in place, We'll measure the voltage across the collector resistor, and here we're saying about 3.79 volts. So that's 3.79. Let's grab the transistor with the low beta, stick that in there, get all the pins in the right holes, and that's showing about 3.67. So 3.67 volts. And let's grab the transistor with the very high beta, stick that in there, and measure the same voltage. And now we're looking at, we'll call that 3.98. Was it 98 or 8? Let me go back. See, looks like 3.98. All right, so 3.98 volts. So we can see with this bias arrangement that even between the min and max, the low and high beta values, we've got less than 400 millivolts or so of change, only about 300 millivolts of change in that bias point across all three of those. So quite clearly this bias arrangement is very immune to changes in current gain or beta. So this is a very, very common bias arrangement that you'll see. And that's kind of the design rules, if you will, for this, is to make the current in the bias path relatively large compared to the base current. And then establish, a reasonable voltage across the emitter. In my case, I picked about 0.5 volt. That wouldn't really impact the amount of swing that I've got available here too much by only taking 0.5 volt away, but it also gives me the ability to set up the bias current in a nice fixed way. So we've got a nice fixed bias across the collector resistor. I hope these examples have shown you how the choice of your bias network can really affect how well your circuit will be independent of the beta value of a transistor, and that there's a lot of value in putting in a slightly more complex bias arrangement to give you beta independence so that the circuit would be easy to replicate and duplicate for larger volumes in different transistor types. What I'm going to do next is just go through a little bit of the derivation or the math behind each of these so we can see a bit mathematically why this is true. In this first, fixed base bias case, it's actually quite simple. The base emitter voltage is basically fixed. At these low bias values, it's about 0.6 volts. So the current in the base resistor is just simply the VCC minus VBE over that resistor value. That gives me the base current. And then the current flowing in the collector is simply going to be the base current times the beta, the beta value at that particular current level. And then obviously that current through this resistor creates that voltage drop. And of course, given that this voltage drop here is entirely dependent on the collector current, which is just beta times IB, you have a direct dependence of the voltage across that collector resistor to beta. So a change in beta is going to cause a change in that collector voltage. Very simple, and it's why it's really the worst choice to use to make a circuit that is independent of beta. Now with the collector feedback, as we mentioned, as the beta varies, it's going to also kind of vary the amount of voltage that appears across this base resistor. So the math is a bit more involved. I won't go through all of it, but I'll leave it here so you can jot it down and play with it yourself. But if you think about just writing out some equations, we know that the base emitter voltage is about 0.6 volts. The voltage across the base resistor is just the base current, whatever it happens to be, times this resistor value. So that gets us to the voltage here. The voltage across this guy is going to be equal to essentially the collector current plus the base current, because the collector current's going down here, the base current's going down here, so the sum of them is going through this resistor here. So therefore the voltage across that resistor is equal to essentially beta plus 1 times IB, right? Because it's IB plus beta IB. That's the total current times RC. So we can write out some equations saying that VCC is equal to the sum of those three voltages. Okay, and if we rearrange that, we can come up with this equation for the base current. It's simply VCC minus VBE, okay, VCC minus VBE, divided by RB plus beta plus 1 times RC. And of course, the collector current is just beta times that value, so we put a beta up there. So if we want to look at the voltage across RC, that's essentially just RC times beta plus 1, right? RC times beta plus 1 IB. So it's RC times beta plus 1 times IB. And if we look at this equation, we can see we see beta in both the numerator and the denominator. So that's going to tend to reduce the dependence on beta, but it does so as a function of the difference or the ratio of RB to RC. Think about the extreme case where RC goes to 0, then VRC equals 0, and nothing's going on. Or if RC were very large. If RC were very large compared to, or I should say if beta times RC is very large with respect to RB, RB would come out of this equation, and you're left with a relationship that says that VCC minus VB over RC determines what that voltage is. But the reality is we live somewhere in the middle. So we're still going to have some beta dependence, but it's reduced compared to what it was in that fixed base case. Of course, now the idea with the voltage divider bias is to essentially take IB out of the equation. So we start off making a couple of assumptions. We're going to basically make the current through R1 here much greater than IB, 25, 50 times RB or even more, depending on how much current you can afford to burn in this simple resistor divider stack. So the larger you make that with respect to IB, the less dependence you're going to have. So by doing that, we can basically say that the current in R1 is basically equal to the current in R2 because IB is somewhat negligible relative to that current. We could also make the same basic assumption that the current in the collector current is basically equal to the emitter current because beta, if it's 100 or more, we're only talking about a 1% difference between those currents. So there's some nice simplifying assumptions and approximations we can make. So given all that, we're just going to set up a bias voltage using or a bias using the emitter voltage and this emitter value. So let's pick what emitter voltage we want. 500 millivolts is a pretty good starting value. Gives me enough voltage across here to make me a bit independent on VBE variations and other things. So it's a nice little starting point and doesn't steal too much headroom away from the available swing for the transistor. So it's a nice starting point. Now for an we already established from our requirements we wanted a collector and thus emitter current of about a milliamp. So we want about 500 ohms. I've got 470 in my circuit because that was a quick value I had on hand in my junk box to put together. So now I've established what that resistor is. I already knew my requirement wanted 3.9K here. So okay, if I've got a half a volt here and I've got 0.6 of a volt across here, that means that the voltage at the base is going to be 1.1 volts. So now I know that I want this current to be 50 times or so base current, and I want 1.1 volts here. That's a simple resistor divider. I'm not going to go through the math for that. We'll just say that VB, or the voltage at the base, we want to be 1.1 volts. And let's say about 50 times IB. That'll kind of tell us what the total current is here, or VCC over the sum of R1 or R2. So that gives us in the neighborhood of about 20K. So I figured, well, let me just start with a 20K resistor here, and then I calculated what resistor I needed here to give me 1.1 volts. Again, simple voltage divider calculations. And so in setting that up, we now have got a circuit that gives us pretty darn close to a fixed value across this resistor, even with wide variations in beta of that transistor. Anyway, I sure hope you enjoyed watching, and thanks again for being there.